It's my great pleasure to present this joint work with Larry Wasserman and Sivaraman Balakrishnan. It was recently accepted into the proceedings of the National Academy of Sciences, PNAS. Larry and I are now co-advising a student, Robin Dunn, who is kind of extending this work and looking at some future directions. So I'll briefly mention some interesting simulations that she's also done recently. Okay, so here's the high-level summary of the talk. For irregular models, we should use what I'm going to call the split likelihood ratio test instead of the likelihood ratio test. I will describe what that is soon. We can invert the test to get a universal confidence set. Interestingly, for regular models, the LRT and the split LRT behave somewhat similarly. We can do model selection using sieves. The split LRT will be a randomized test, but we can de-randomize by averaging. We can run it sequentially, what we call the running-MLE likelihood ratio test, and create a confidence sequence for it. And finally, we can use the Ripper split LRT when we're dealing with convex sets of densities, and I'll mention a few other extensions as well that could be of interest, like profile likelihoods or powered likelihoods or mixture likelihoods and so on. Okay, so let's get started with the first part where I just explain what the split LRT is. So as a quick recap, for regular models, the likelihood ratio test is easy. Okay, so this is just so that we're on the same page with notation. Assume that the data y1 to yn is drawn from some distribution with a density p theta star, where theta star will be the ground truth for most of this talk. And this is for some theta star in a set script theta that's pre-specified. Even though I've written things here in a parametric language, we'll see that later on we can do things non-parametrically as well. So here, assume that we are testing that theta star is in theta naught against an alternative that theta star is in theta 1, which we usually say contains theta naught. Then Wilks' theorem for regular models says that that 2 times the log likelihood ratio converges to a chi-squared d distribution under the null. And so over here, I'm using L of theta to determine to denote the likelihood function. And here theta hat 0 is the MLE under the null, theta hat 1 is the MLE under the alternative, and D is the difference in dimensionality between theta 0 and theta 1. Okay, so this is very standard and well known. So based on this, we use the likelihood ratio test, which rejects if 2 times this log likelihood ratio of alternative to null is larger than C alpha D, where that's the 1 minus alpha quantile of the chi-squared D distribution. Okay, and so essentially, what this is saying is the numerator is the alternative, the denominator is the null likelihood. If the alternative is much more likely than the null, meaning larger than some threshold, then we reject the null. Very reasonable. What we know is that under regularity conditions, the probability of falsely rejecting the null, that is probably that the null is true but we reject, the type 1 error, is at most alpha plus small op1, so it's asymptotically level alpha. Okay, so for regular models, everything is great, the likelihood ratio works well. However, there's a lot of irregular composite testing problems. So here are just 6 examples. The first one is mixtures. For example, let's say P theta star is a mixture of K Gaussians. A second one is shape constraints. We can say that maybe the underlying distribution is log concave. This is a more non-parametric example. A third one that has been studied quite recently is this notion of multivariate total positivity of order 2. And so our null might be that the underlying distribution is Gaussian MTP2 or Ising MTP2. I should just mention that in all of these cases, the likelihood ratio limiting distribution can be extremely complicated. Often we don't know it. And we often don't know a level alpha test using the likelihood ratio test because of the irregular behavior of these models. They're often, there's some boundary behaviors that makes them non-singular because of which the likelihood ratio does not have this kind of chi-squared distribution like Wilks' theorem. A couple more examples are factor models when theta star has k hidden factors or states. A very simple Gaussian conditional independence testing problem where the null is that x1 and x2 are independent, and the alternative is that x1 and x2 are independent given x3. And all of these are situations in which actually it's not easy to apply the likelihood ratio test. We don't know of a level alpha test so far. But one thing to notice in common, and that we will exploit, is that in all of these we can approximately, at least, we can calculate the MLE under the null. So people have developed computationally efficient algorithms for computing the MLE when P is log concave, or when you're dealing with a hidden Markov model, or variants of EM for mixtures. So we're going to leverage the fact that we can calculate the MLE under the null and propose a new test. Okay, so what is it? Here it is on one slide, the split likelihood ratio test. The first line is just recalling what the usual likelihood ratio test does. This is what we propose to do. And this works for any model, not just for regular models. Okay, so split the data into two parts, D0 and D1. Now, the split likelihood ratio test is going to reject if something very similar to before, okay, it looks like 2 times log likelihood ratio, is larger than a different threshold 2 log 1 over alpha. Okay, but it's kind of important to pay attention to what these are. In the numerator and the denominator, I have this term L0, which is just the likelihood on D0, just the first part of the data. So the second part of the data doesn't appear when taking the likelihood L0. It appears when calculating the these estimators theta hat 1 and theta hat 0. So theta hat 1 is any estimator. It doesn't have to be the MLE. It could be a Bayes estimator, a robust estimator, but that's calculated under the alternative as before, but it's calculated on D1. And theta hat 0 is the maximum likelihood ratio estimator under the null, but on D0. Okay, so when we go back to this, expression over here, the likelihood is evaluated on D0, but we use theta hat 1, which is calculated on D1, and theta hat 0, which is calculated on D0 itself. Okay, so slightly odd test, but that's what it is. But amazingly enough, under no regularity conditions and no asymptotics, the probability that under the null we falsely reject is at most alpha. So this gives you a level alpha test as long as you can calculate the MLE under the null. This is a reduction from maximum likelihood estimation to testing. Okay, if you can calculate the MLE under the null, you can test the null. And because under the alternative, you can use any estimator. All right. So let's think about this a little bit more. Why is the split LRT valid without assumptions? Again, this is just a summary of the first part. Is the top is just a summary of the previous slides. We say split the data, calculate this split LRT statistic, and test, and that's our claim. So the claim is proved in one line. So let's look at that. So let's look at the expected value under theta star, which is from the null. The null is a composite set. Okay, this is a composite null testing problem. The unknown null is theta star. We're looking at the likelihood, the split likelihood ratio statistic. Okay, so the first thing to notice is that in the first inequality, I've just substituted theta star in the denominator instead of theta hat 0. And the reason is simple. Theta hat 0 is the maximum likelihood estimator. So L0 of theta hat 0 is larger than L0 of theta star. So this is just using the fact that theta hat 0 is the MLE. Then we just literally expand out what is what is this expectation. It's over only the data set 0, so that's why this product over only IND 0 is there. And then it's easy to see that this just equals 1. Okay, so what we have is that this likelihood ratio statistic, its expectation is bounded by 1. And we can apply Markov's inequality to say that, well, this it's also a non-negative random variable. So the probability that it's greater than 1 over alpha is at most alpha. Okay, and you can see that our likelihood ratio, a split LRT, the way I defined it was in terms of logs. All I did was to make it look visually similar to the original likelihood ratio test, I said we reject if 2 times the log likelihood ratio is larger than 2 times log 1 by alpha. But the proof just is Markov's inequality. But I like to think of this as, even though you think, oh, it's just Markov's, you're not using much, so it must be trivial. Maybe the test is trivial because you're only using Markov's inequality. Well, we are just using Markov's inequality in the same sense that the Chernoff bound just uses Markov's inequality. It's important to note what we are applying the Markov inequality to, right? And so essentially the way I perceive it is that the quantity of interest is not the likelihood ratio statistic, it's the log likelihood ratio statistic. And so what we're really applying the bound to is to the exponential of the log likelihood ratio statistic. So we are bounding, so this line over here really should it should be read as it's bounding the expectation of the exponential of the log likelihood ratio, like we would do in bounding the MGF of a random variable. However, instead of showing that the random variable is sub-Gaussian or something like that, we bound this exponential of the log likelihood ratio, which is bounded by 1. So that's why I'm calling it a poor man's Chernoff bound. But we really are controlling the tails. We are really using the fact that this has exponentially decaying tails, and so this is not a trivial Markov's inequality, as we will further see. Okay. So just a note that I've presented everything from the point of view of testing, but you can invert the test to get a universal confidence set for the unknown theta star. Okay, so here's the AN is the usual likelihood ratio based universal, not universal, sorry, just the usual likelihood ratio confidence set. You just take 2 times the likelihood log likelihood ratio, and you include all theta, for which that is at most C alpha D. So this is just standard inversion of the test. And then the guarantee is that theta star will be contained in AN with probability at least 1 minus alpha asymptotically. Then just compare that now instead to our definition Cn of the universal confidence set. Here we're just inverting the split likelihood ratio test. And so it looks visually similar to above, except that we use 2 log 1 by alpha instead of C alpha D, and the numerator theta 1 hat is on a different data set, while in the usual likelihood ratio test, theta 1 hat is on the same data set. So that's the other difference. And then under no regularity conditions and no asymptotics, the probability that theta star is contained in Cn is at least 1 minus alpha. Okay, so again, here's a different sense in which this Cn is actually a non-trivial universal confidence set. For regular models, let's say fixed D, fixed alpha, both diameters of An and Cn are 1 over root n in diameter. So that's so Cn has the same rate in some sense at which it shrinks to 0. And for high-dimensional Gaussians, you fix alpha, you send D to infinity. Turns out that Cn is about 4 times wider than An. So even in the high-dimensional setting, it's doing something actually very reasonable. Clearly, we're losing some constant, but the point is that for irregular models, we have no such universal confidence set. We have no such universal test. So at this point, we would like to save on that constant, but we would also like some test that works without assumptions, without asymptotics. Okay, so continuing where I left off, it turns out that we don't actually have to maximize the likelihood. There are some cases in which maximum likelihood estimation could in fact be computationally hard, but we can find often convex relaxations, I'm going to call it F theta, which can be optimized. So over here, the condition we will require is that we have a slightly different domain. You might, for example, take your null set and expand it because it has a larger domain for F. That's fine. What we need is that it's a relaxation in the sense that the maximum of F over this domain is larger than the maximum of L. So this is just this is the likelihood using the function capital F. And as long as you achieve a larger value, we're going to call that a relaxation. So you can call theta hat 0 F as the maximum relaxed likelihood, and then you can use the relaxed split likelihood ratio test as I've defined over here, which might be more suitable in in settings in which computing the MLE is computationally hard. So an example would be the stochastic block model, for which we know that there are semi-definite programming relaxations which could be efficient, but maybe the original MLE problem is harder. Okay, and again, the same guarantees go through. Under no regularity conditions, we have type 1 error control. Okay, we don't just have to stop with testing. We can go from testing to model selection using sieves. So now assume that you have a nested model, P0 subset of P1 subset of P2 and so on, and that this P star, the true underlying distribution, is in Pj star for some smallest index J star. So idea of sieves is simple. You just test the null H0J, which is that P star is in Pj. You test it one by one for J is equal to 1 and 2. And in our case, we test it using the split likelihood ratio test. And we stop at step J hat, which is the first time we fail to reject the null. Okay, so we test J equal to 1. If we reject, we try 2. If we reject, we try 3, and so on. Keep applying the split likelihood ratio test at each step. And so this could be used to test, for example, how many mixtures are needed. And so then the guarantee that we have is that J star is at least J hat, which means we don't go past J star with high probability. That is, the probability that P star is in P J hat minus 1 is at most alpha. All right. So important point is that we don't need to correct for multiple testing. Even though we're testing a sequence of hypotheses, only one of them is a true null. Before that, when we test, all of those nulls are not true, so we can't make a false positive error. At one step, which is J star, the null is true, and at that step, we will fail to reject the null with high probability because the null is true. And with high probability, we'll stop them. So we don't actually have to correct for multiple testing. So that's nice. Okay, I mentioned before that this is a randomized test. We split D0 and the data into D0 and D1 at random, but we can de-randomize by averaging. It's extremely simple. Remember that the only thing we really used was Markov's inequality. So the expected value of the statistic was at most 1. It turns out that, for example, we can apply the CrossFit LRT in which we swap the roles of D0 and D1. Average the two test statistics that you get with D0 D1 and with D1 D0, average them. And because each expected value was at most 1, the average statistic also has its expected value at most 1. It leads to a valid test. Completely straightforward. And definitely we find that in practice, just even one swap improves performance a lot. So at the very least, I would apply the CrossFit LRT. But you can do a k-fold version of this where you split into k parts, use k-1 parts to calculate theta 1 hat, calculate theta hat 0 on the last fold, and evaluate the statistic on the last fold, and then average across all folds. Or you can swap the role of what you use the k-1 splits and 1 split for. There are many variants of this. You can also do all splits. You can consider all possible splits or permutations of size n over 2 if you want. And so it seems like all of these are valid tests under no regularity conditions. In our preliminary experiments, it seems there is a computation statistics trade-off. So Robin produced some beautiful plots for us. So this is in the case of a Gaussian, which is of course a regular setting, but it helps to see what does our test do compared to the usual likelihood ratio test. So here we are plotting the confidence set produced, and we just draw from a two-dimensional Gaussian, and then we produce the usual LRT type set, and we produce the set from the split LRT, which is this bigger yellow circle, the CrossFit LRT, which does just one swap, which turns out to look like this red rugby ball. The subsampling base, where we do just many subsample runs, so we repeat the split like many, like 100 times, and that's the blue one. And then the usual LRT is it's the tightest, it's the black one in the middle. And so actually we can prove phenomena that you're seeing over here. We can quantify the algorithmic variance. We can quantify the statistical variance. We can prove that the subsampling based confidence set is tighter than the split one. The cross fit is, so we can relate all of these. And what I had mentioned earlier was that in the high dimensional setting, the yellow circle is at most 4 times larger than the black circle. That's what I had said earlier. We lose a constant factor, but it turns out that the constant factor is much smaller for subsampling. So it's, if I remember correctly, it's that it's about half the price you pay, or even less. So we have all of these in forthcoming work, but I think this is at least an interesting simulation to see that it's even in a regular setting, it's doing something quite interesting. But of course, we're most interested in irregular settings. Okay, so I should mention that everything I've said so far is in this batch setting where we just have one batch of data and we want to run one test. But it turns out that we can apply this test sequentially. And in fact, to be honest, from my perspective, this is where everything started from. Over a dinner with Larry, I mentioned to him that we can test we can test composite nulls. We can form confidence sequences for in highly non-parametric situations, and the idea is very simple and so on. And I think Larry took it from there and said, wow, if you can do these things in a sequential setting, then we can do them in the batch setting to solve problems we didn't know. And so somehow for me, everything started from the sequential setting. This is how I still think about it. So let me explain what the sequential point of view is, and maybe some of you will find it useful as well. Okay, so what's the idea? The idea is that if you fail to reject the null, then you can actually collect some more data, d nu, and we can update the test statistic in a particular way that I'll describe, and we can check again if it's larger than 1 over alpha. And we can keep repeating this indefinitely, and we do not need any multiple testing correction. It's like a sequential likelihood ratio test of Wald, except a version that works for composite null hypotheses and so on. Okay, so I'll present the simple special case that corresponds to getting one data point at each step, and we call this the running-MLE likelihood ratio test. And so this is what it does. It's a little bit subtle again. I'm defining this process MT, one for each time, and the denominator theta hat 0t is the MLE as before, using all the data points up to t. Okay. Now the numerator is more interesting. It's what's called a non-anticipating estimator, where you evaluate the likelihood of yi using all the data up to I minus 1. So in this product in the numerator, you have p theta at 0 of y1, p theta hat 1 of y2, p theta hat 2 of y3, and so on. In the denominator, you just have this p theta hat 0 of y1 and of y2 and of y3. So slightly different things going on in the numerator and the denominator. And amazingly enough, you can run this sequentially, and under the null, you will never reject with high probability. So even though you're running technically an infinite number of tests one at a time, with high probability, you'll never reject. The probability under the null that there exists any time t, that such that you reject at time t, is at most alpha. So you get non-asymptotic type 1 error control with no assumptions. Okay, and the reason that this is true is because this MT that I've written down here is actually upper bounded by LT. LT is a quantity that only appears in the proofs, but LT is a non-negative martingale. And what LT is in the denominator, instead of theta hat 0, it substitutes theta star. And so, of course, we don't know theta star, so we don't know LT. But it's very easy to see that LT is a non-negative martingale, and MT is upper bounded by LT. We apply something called Wheel's inequality to LT to prove that the probability that LT crosses 1 over alpha is at most alpha, and MT is only smaller, so the probability that it crosses 1 over alpha is also at most alpha. So it's a short proof. Okay. Great. So it turns out that you can also construct a confidence sequence for theta star, not just run a sequential test. So I'll explain what that means. So as before, we can invert the sequential test. We can form this quantity CT, which is a confidence set, which is the set of all theta, such that the quantity I mentioned on the previous slide, this 2 times log sequential split likelihood ratio statistic, is at most 2 log 1 over alpha. Where remember again, the numerator is this non-anticipating sequence of estimators, and they can be any estimators. They don't have to be the MLE. Earlier, the denominator was the MLE, but when you form the confidence set, you can just put in different points theta, and that's fine. Just a standard inversion. Then what we have under no regularity conditions is that simultaneously over all of time, CT contains theta star. Okay, so the probability under theta star that for all t from 1 to n, theta star is in CT, this probability is at least 1 minus alpha. So it's simultaneous coverage over time. And an equivalent way of saying this is that for any arbitrary stopping time, which could be a data-dependent stopping time, which you don't have to specify in advance, C tau, that the confidence set at that stopping time tau, will contain theta star with high probability. The probability that it does not contain, probability that theta star is not in C tau is at most alpha. Okay, so you get correct, valid error control even at stopping times. And this is again without assumptions, non-asymptotic, everything. Great. All right, so a quick, interesting class of examples which I like thinking about. This is the case of a convex class of null densities. So most sets of most null sets are not convex in the sense of a mixture of those two distributions need not lie in there. For example, a log concave, a mixture of two log concave, a mixture of two Gaussians, for example, is not a Gaussian. So a mixture of two log concave distributions need not itself be log concave. But there are sometimes some other sets of densities which are actually convex, and we give some examples in the paper. So in that special case, you can construct a different test, which I'm calling here the Ripper split LRT. So the difference is here that in the denominator, in the null likelihood, I'm not substituting the null MLE. I'm instead substituting this arrow of theta hat 1 to theta 0. And what this is the reverse scale projection of theta hat 1 onto theta 0. So it's an interesting thing. So you first calculate theta hat 1 anyhow you want, it's any estimator. And then you do a reverse scale projection of theta hat 1 onto the null set. So it kind of finds the nearest point on the null set to theta hat 1. And so the test uses that. So we call this the Ripper split LRT. It's inspired by some recent work by Wouter Kulin and Peter Grunwald. And so what is the guarantee that this test has? If this set of, if P theta is a convex set, or under the null, at least under theta 0, that's a convex set, then the probability of rejection is at most alpha. Okay, and the reason is a very interesting theorem by Lee. Lee was Andrew Barron's PhD student and in Yale, and he graduated in '99. And in his PhD thesis, he proves this very interesting theorem. I mean, of course, he doesn't state it like this, ready for us to use. He states it slightly differently, but this is basically what it boils down to, which is kind of what we needed to apply our Markov inequality. He proves that under theta star, so it's like a triangle kind of setting. So the truth is coming from theta star. We use theta hat 1 in the numerator. We use the Ripper projection of theta hat 1 in the denominator. And under theta star, this likelihood, this split likelihood ratio has expectation at most 1. Okay, so this fact is non-trivial, and it's from Lee's thesis. Okay, so in the convex case, the Ripper split LRT, it does dominate the maximum likelihood estimate based split LRT, but it requires calculation of this reverse scale projection. As far as I know, it's not easy to calculate this quantity. The MLE, we have thousands of cases where we have put in decades of, or a century of work into calculating the maximum likelihood estimate under lots of situations. And so our universal test is immediately applicable. The Ripper test, it looks interesting, but I think it's going to need more work on algorithms to actually compute this efficiently in interesting settings. As a side note, we can also prove something on the model misspecification front. Suppose the data comes from a set that we're not considering. So it comes from Q, which is not in our set theta. Well, if the Ripper of Q, if the projection of Q is in theta, then the universal set will contain this Ripper with high probability. Okay, so essentially it's saying that if Yeah, it won't contain Q because our universal set won't contain Q. Q is not in the set we're considering, but it will contain this kind of scale projection onto the set, which is somewhat natural. Okay. There are some other extensions that we point out in the paper. If there are nuisance parameters, there's a version of this that uses a profile split likelihood. If you have somewhat less belief in your likelihood itself, in the Bayesian community, people have shown that raising the likelihood to some power less than 1, this is called sometimes the powered likelihood approach. It adds some robustness to these Bayesian procedures. But it turns out that you can use a powered split likelihood if you want, and that works. It gives you correct type 1 error control. It gives you a martingale and things like that. So that you can add robustness by raising the likelihood to a power. There are situations in which the likelihood itself is very badly behaved. Even the split likelihood could be. You might want to smooth the likelihood by using a kernel. And so we show that a smooth split likelihood also works out if that's more suitable. And there are conditional versions of this as well. We didn't need the data to be actually IID from some distribution in order to run the test. You could have been getting non-IID data. As long as you can calculate a likelihood, as long as you might want to condition on the past and things like that. This might be useful when you're sampling without replacement, where it's not IID sampling, but there is some kind of conditional independent structure. As long as you can calculate a likelihood, you're good. And so you can apply this in some conditional settings as well. Okay, so just to summarize again, for irregular models, we suggest that you use the split LRT instead of the LRT. We can invert the split LRT bit to get a universal confidence set. They're similar for regular models. They both shrink at a 1/√n rate. For the Gaussian, high-dimensional Gaussian case, at least, it's about 4 times the universal set using our method is about 4 times larger than the usual LRT setting. You can do model selection using sieves. You can de-randomize the test by averaging. In fact, that's what we recommend in practice, that you run the CrossFit version, or if you have some more computational time, then do a few subsamples and repeat this and average all of those, and it helps a lot in practice in our initial experiments. You can run this sequentially to do a sequential test of complex composite non-parametric nulls. You can compute confidence sequences. So, for example, you can compute a sequence of confidence sets that contains the true log concave density simultaneously over time, and you get validity without assumptions. And if you have a convex set of densities, you can use this variant called the Ripper split LRT when it's computable. And there's all of these other extensions that I described on the previous slide. There's plenty more work to be done. For now, this is just a valid test. This is the first step. Somehow in testing, you first want a valid test, then you want to analyze its power. But all of that is open. So we know almost nothing about the power of this test in all of these irregular settings. And so I think analyzing it for mixtures, for MTP2, for factor models, I think all of these will require kind of their own efforts, and we hope that the community at large picks up their own favorite problem, tries to see what is this test doing for their problem. It likely won't be trivial to analyze the power, but at least now we have a valid test that people can use in practice. Okay, with that, I'd like to thank my collaborators, Larry, Siva, and Robin again, and I'd like to thank all of you for your attention. Okay, thank you.